we're going to determine if the infinite series sum as I goes from 1 to infinity, a half to the I, converges. If it does, then we're going to give the limit. So first step, we're going to look at the sum as I goes from 1 to infinity, 1/2 to the I, and we'll write out the first few terms to get a feel for the series. It's 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th, and this will go on indefinitely. So writing it out, it's 1/2 plus 1/4 plus 1/8 plus 1/16, and this goes on indefinitely in that form. Now this was our first step. We are given this infinite series. Our second step is we are going to create the sequence of partial sums S of n as n goes from 1 to infinity. So we're going to come up with a formula for what the sum of the first n terms of this series are. So S of 1 is a half, S of 2 is 1/2 plus 1/4, which is 3/4. S of 3 is 1/2 plus 1/4 plus 1/8, which is 3/4 and 1/8 is 7/8. S of 4 is a half plus a 4th plus 1/8 plus a 16th. 7/8 and 1/16 is 15/16. So I can see the first term of the sequence is 1/2. The second partial sum is 3/4. The third is 7/8. The fourth is 15/16. Working this, we see that when n was 1, the first partial sum was a half. When n was 2, the second partial sum was 3/4. When n was 3, that partial sum was 7/8. When n was 4, that partial sum is 15/16. So working this in general, when it's n, the sum of n terms, I see the pattern that the denominator is 2 to the n and the numerator is 2 to the n minus 1. I now have a formula for S of n. S of n is 2 to the n minus 1 over 2 to the n. So my sequence of partial sums from 1 to infinity is just the sequence of 2 to the n minus 1 over 2 to the n as n goes from 1 to infinity. Now that I have a formula for the sequence of partial sums, my last step is to take the limit as n approaches infinity of that formula, because that's partial sum sequence. If that limit exists, then that is the limit of the series. So I am doing the limit as n approaches infinity, 2 to the n minus 1 over 2 to the n. And really, we're really doing this as x. So I'm really doing the limit as x approaches infinity, 2 to the x minus 1 over 2 to the x, because that would be a continuous function there. Now I'm working this limit, the limit as x approaches infinity, 2 to the x minus 1 over 2 to the x is 2 to the huge infinity, 2 to infinity, which is infinity over infinity, which I now can use L'Hopital's rule. I put the LH, and it is the limit as x approaches infinity. The derivative of 2 to the x is 2 to the x log 2 minus 0, but the derivative of 2 to the x on the bottom is 2 to the x log 2. I simplify, I always do that after L'Hopital's rule, and I get the limit as x approaches infinity of 1, but the limit of a constant is just a constant. Now that we've done this, that's our last step, and what that means is that the series as I goes from 1 to n, not to n, 1 to infinity, 1/2 to the I, its limit is 1. That means it's an infinite sum and it converges to the value of 1.